Yes. So welcome all students. Today we are going to start another class related to the transformer. In the last class, I have given you a description about the practical transformer or non-ideal transformer when it is under the no load condition. And what we have got from the study that under practical condition, the transformer draws a no load current I naught, and this I naught composed of consist of two components. One is called core loss component, another is called magnetizing component. And I have also uploaded a video which is being titled as an open circuit test on transformer. We can calculate these two values, the I naught, the IM, the IE component from the open circuit test. I will explain this test in the theory class also, but from the practical it is very clear that we can calculate it, we can find out it, observe it, and then we can calculate the IM and IE component. We can also calculate the corresponding equivalent circuit parameter at no load condition, that is RE and XM. That I have also demonstrated you in the practical class. I think so no problem is there. Today what we are going to do that yes, my screen is visible.
Yes, sir.
Okay. So you can see in my screen, the topic is today transformer on load. When transformer is loaded by certain load like resistive, capacitive, inductive, then how it will behave here. So far what we have studied, अभी तक हमने क्या पढ़ा है कि एक ट्रांसफॉर्मर था जिसको हमने आइडियल माना और उसको नो लोड पे ऑपरेट किया, तो हमने मालूम पड़ा कि उस केस में हमने ये देखा कि हमने कई चीज़ें नेग्लेक्ट की. हमने एज्यूम किया वो जीरो है, जैसे लॉसेस हमने जीरो माने तो इनपुट पावर इज इक्वल आउटपुट पावर माना. फिर उसके बाद हम एक स्टेप और आगे बढ़े और हमने कहा कि नाउ ट्रांसफॉर्मर इज नो लोड आइडियल बट इट इज अ नॉन आइडियल और प्रैक्टिकल ट्रांसफॉर्मर बट इट इज बीइंग केप्ट ऑन नो लोड, that is secondary is kept open. Then we found that it will draw a no load current I naught, and later on we have make a mathematical analysis, found that this I naught consists of two components, IM and IE, and corresponding to IE and IM there is a corresponding equivalent no load parameters which are connected in parallel. We have two parallel branches for no load circuit on the primary side, that is RE and XE. RE and XE, the inductive reactance and the resistance. Okay. Then we have also calculated that the so-called the power drawn, at the no load condition is generally the iron loss, the constant loss. Is it clear? So we have found out the iron loss also, we have found out the different parameters also. Okay, now one important thing, that this experiment which I have dealt in the practical class, okay, then this is always performed, that the open circuit test is always performed at a rated voltage, Now we come to another topic called transformer on load. Okay, transformer on load, where some load is being put. Now at present I will not tell you that which type of load is there, because load can be of any type. एक रजिस्टर अगर हमने लगा दिया तो रजिस्टिव लोड हो गया, एक कैपेसिटर लगा दिया तो कैपेसिटिव लोड हो गया, और एक इंडक्टिव लोड लगा दिया तो हमारा इंडक्टिव लोड हो गया. ठीक है, इंडक्टर लगा दिया तो, लेकिन इसके कॉम्बिनेशन भी लगा सकते हैं. तो अभी हम सिर्फ कहेंगे ट्रांसफॉर्मर इज लोडेड. सो व्हाट हैपेंस? So when I say transformer is on loaded condition, it means that the secondary of the transformer is connected to the load. Is it clear? Now this load I have already explained you can be a resistive, inductive or capacitive or their combination. So what will happen? What will happen when you are loading a transformer, that is secondary of the transformer is loaded with some load like resistive, inductive, capacitive, some secondary, the secondary winding of the transformer will draw some current, and this current will be termed as an I2. This current will be termed as an I2. Okay, and the magnitude of this secondary current, that is I2, that depends upon the terminal voltage V2 and the load impedance. ठीक है, ये जो आपका सेकेंडरी करंट ट्रांसफॉर्मर में आएगा, that is I2. इज इट क्लियर? जब भी आप लोड करेंगे ट्रांसफॉर्मर पर एक लगा देंगे तो एक I2 करंट फ्लो होगा, और ये किस पे डिपेंड होगा? दिस इज डिपेंड अपॉन द अप्लाइड that is voltage, secondary voltage V2 and also on the load impedance. ठीक है, वो लोड जो है वो उसका impedance कितना है, वो केवल R है या R प्लस JX है या R माइनस JX है या R प्लस माइनस JXL माइनस XC है, वो जो भी उसका इम्पिडेंस होगा उस पे, और जो टर्मिनल वोल्टेज V2 आया है उसके ऊपर डिपेंड करेगा उस करंट का. ठीक है, और उस I2 का फेज एंगल कितना होगा, डेट ऑल्सो डिपेंड अपॉन द करंट एंड वोल्टेज, और डिपेंड्स अपॉन द सेकंड फेज एंगल बिटवीन सेकेंडरी करंट, वो डिपेंड ऑन नेचर ऑफ द लोड. लोड किस टाइप का है? इंडक्टिव लोड है तो इंडक्टिव लोड है तो जो करंट है, दैट करंट विल लैग बिहाइंड द टर्मिनल वोल्टेज V2. और अगर मान लो कैपेसिटिव लोड है तो करंट विल बी लीडिंग द टर्मिनल वोल्टेज V2. And if it is a resistive load, pure resistive load, then the current will be, the secondary current I2 will be in phase with the V2. बिल्कुल क्लियर है कि यदि मान लो ये मेरा वोल्टेज है V2, इज इट क्लियर, और अगर मुझे लैगिंग दिखाना है तो मेरा करंट इधर होगा. इज इट क्लियर? दिस इज I2. ये मेरा फेजर डायग्राम, बिकॉज नाउ फेजर डायग्राम इज वेरी इंपॉर्टेंट. अगर मेरा लीडिंग होगा तो मेरा करंट ऐसे हो जाएगा. ठीक है, प्योर कैपेसिटिव है तो ये 90 डिग्री हो जाएगा, प्योर इंडक्टिव है तो ये 90 डिग्री हो जाएगा, रेजिस्टिव इंडक्टिव मिक्स है तो ये कुछ एंगल बिटवीन 0 to 90 डिग्री होगा. आपके रेजिस्टिव कैपेसिटिव है तो ये एंगल समथिंग लीडिंग में होगा लेकिन 0 to 90 डिग्री के बीच में होगा, और प्योर रेजिस्टिव है तो हमारा करंट इन फेज विद द टर्मिनल वोल्टेज I2 होगा. ठीक है, ये चीज आपको समझ में आएगी नहीं. दिस इज वेरी इंपॉर्टेंट एंड दिस इज सर्किट थ्योरी कॉन्सेप्ट, and the same will be utilized here in understanding the transformer phasor diagram when transformer is on loaded condition. Is it clear? I think so. This much is very clear. If you have any doubt, please ask me. Okay, fine. Okay, no doubt means let us move further. So first of all, what will be the value of this I2? So in order to explain this, let us move to the first of all our previous knowledge, that is when the transformer is kept, the transformer secondary is kept open, that is transformer is no load. So when the transformer secondary is open, what was the phenomena happening? Let me revise you. Okay, that because I have already explained you, but again it will be coming. So I have applied an voltage V1. You see, this is the V1 is the applied voltage. So what will happen? When it is under no load, means that secondary is open. Secondary is open, no load is there. See, okay. So the current I0 will start flowing through it. Now when current I will flow, a magnetic flux will be produced. Okay, flux will be produced and a corresponding induced EMF. This magnetic flux, which is common to both primary and secondary winding. The primary has N1 turns, the secondary is N2 turns. It will link. So induced EMF is produced in both primary and secondary wide. Its value is E1 and E2 respectively. Okay. So basically when no load current flows, okay, the no load current produces a magnetomotive force, MMF. Okay, you might have learned the basic concept of the magnetic circuit, that just as you have EMF, a voltage source, in order to develop a current, so in order to develop the magnetic flux, we should have a magnetic motive force MMF, and which is nothing but equal to number of turns and the product of the current. So here the number of turns on the primary are N1, okay, and the number of turns are into N2. So how much there will be some current, that is N1 phi naught current will MMF will be produced, and this MMF will link both secondary and secondary and primary winding. Okay, so what happens due to this, and this is varying in nature. Why this is varying in nature? This flux is varying in nature because the applied voltage is sinusoidal. The applied voltage is sinusoidal, or in short, or in general, I can say it is AC voltage is being applied. So AC voltage, AC current, AC flux, varying flux. This flux will induce an EMF both in primary and secondary winding, E1 and E2. I think so this concept is very clear. So this is the circuit diagram which I have shown you. This is of the no load. Okay, because I am again revising it because this will be coming in your the so-called how transformer operates when it is under loaded condition. Now with this much of background, so let us discuss the operation of a transformer load condition. So when the secondary is kept open, it draws only no load current. Okay, and when load is connected to the secondary of the transformer, what happens? I have already explained you, I2 current flows. Now you first of all don't worry about that, sir, ये load किस type का है. Don't ask any question at present. I will tell you later on if it is resistive load, how it will behave, if it is capacitive load, how it will behave, if it is inductive load, how it will behave. Let us assume that some load is being connected. You can see a load is being connected. Now as soon as you connect a load, a secondary current I2 starts flowing through it, and we will get a terminal voltage V2. We will get a terminal voltage V2. Clear? So what happened? What happened? Now when the secondary current flows I2, now this current, this E2, now look towards the diagram, this E2 is being generated due to the flux produced by the primary current I0. Okay, but now a secondary current is start flowing it. So how it will move? It will move like this. So the secondary current will flow in the secondary winding also. So when it will flow in the secondary winding, it will also produce an MMF. And what will be the value of this MMF? This value will be equal to N2I2, because number of turns on the secondary are N2, because MFF is defined as number of turns and the current flowing through that winding. So current flowing is I2, that is secondary current, and number of turns on the secondary is N2. So MMF magnitude will be N2I2. Clear? Now what happens? Previously a flux MMF was there because of the primary winding, and now there is another MMF because of the secondary winding. Now this force set up a flux phi2. So previously we have a common flux phi. Now another flux is being produced. तो एक तो प्राइमरी वाइंडिंग के कारण फ्लक्स हो गया था फाई, और अब जैसे ही लोड किया तो एक अनदर फ्लक्स प्रोड्यूस हो गया हमारा, जिसको हम कहते हैं फाई 2. सो टू टाइप ऑफ फ्लक्सेस आर देयर नाउ. वन इज फाई एंड अदर इज फाई. नाउ दिस फाई 2 अपोजेस द फ्लक्स फाई. क्यों? लेंज लॉ क्या कहता है? लेंज लॉ कहता है कि द इंड्यूस ईएमएफ फ्लो इन सच अ डायरेक्शन that it opposes the very cause. It opposes the very cause. और cause अभी इसका क्या है? ये cause है secondary current, और secondary current किसके कारण flow हुआ? secondary current flow हुआ E2 के कारण, induced EMF. और E2 को किसने बनाया था? इस phi ने. तो ये इस phi को जो मूल है उसको विरोध करेगा कि how you are standing at my position, I should also flow. So this flux phi 2 will oppose the flux phi according to Lenz law. किसी और नियम के तहत नहीं, इट इज अकॉर्डिंग टू द लेंज लॉ. लेंज कहता है कि जिसने उसको बनाया उसी को वो विरोध करेगा. ठीक है, तो उसका विरोध शुरू हो गया. अब व्हाट हैपेंस नाउ? दिस फ्लक्स phi 2 opposes the main flux phi, and what happens when opposition is there? What will happen to the resultant flux? The resultant flux will decrease, and due to decrease in this flux, okay, what will happen? The common flux is reducing, therefore the EMF E1 will also reduce. EMF जो E1 डेवलप हुआ था, देखो ये E1, यहां देखो. अब इसको कैलकुलेट कैसे करते हैं? अब जो आपका नेट फ्लक्स रहा है, लेट मी एक्सप्लेन यू. व्हेन यू कनेक्टेड अ लोड, नेट फ्लक्स phi will be equal to how much? Let it be phi net. Okay, it will be nothing but phi minus phi 2. So this will be the net flux. So now flux linking is less in comparison to previous 5 only. So what happens? It will reduce. That's what I am saying, that E1 will reduce. Now what will happen when E1 will reduce? The E1 is reduced. Previously under loaded condition V1 equal to E1. Under no load condition V1 was equal to E1, but now E1 has reduced. But since source voltage you cannot reduce it, V1 you cannot reduce it, strength of V1 will be more than E1, and thus what will happen? V1 will provide an additional primary current. Okay, and I will refer it as I1 dash. It will be referred as an I1 dash. तो कुल मिला के आपको समझ में आ गया व्हाट इज देयर, दैट एक सेकेंडरी में जैसे ही करंट फ्लो हुआ, सेकेंडरी करंट के कारण एक एमएमएफ प्रोड्यूसर जिसको हमने phi2 डेजिग्नेट किया, और इस phi2 ने जो मेन फ्लक्स था phi जो कॉमन था दोनों के बीच में उसको रिड्यूस किया, उसको डिक्रीज किया। उस डिक्रीज की वजह से क्या हुआ? उस डिक्रीज की वजह से क्या हुआ कि हमारा E1 रिड्यूस हो गया, लेकिन V1 जो सोर्स वोल्टेज था वो रिड्यूस नहीं हुआ। सोर्स तो अपना वोल्टेज मेंटेन रखेगा, तो E1 रिड्यूस हो गया, तो V1 ने क्या किया कि उसको एक एडिशनल प्राइमरी करंट दिया ताकि वो उस फ्लक्स को मेंटेन कर सके। और ये करंट कितना था? I1 डैश। ये करंट कितना था? I1। यहां आपको कॉमा दिख रहा है मगर बुक्स में आपको ऐसे लिखाई देगा I1 डैश। इज इट क्लियर? तो I1 डैश हुआ। पहले उसमें कौन सा करंट फ्लो हो रहा था? प्राइमरी साइड में पहले कौन सा करंट फ्लो हो रहा था, चाहे वो लोड हो नो लोड हो? कौन सा था? I0। कौन सा था? I0। अब एक एडिशनल करंट और फ्लो हो गया, उसका क्या नाम है? I1 डैश। अरे समझ में आया कि नहीं? इज देयर एनी डाउट? देन यू कैन जस्ट, आई कैन पॉज इट हियर एंड यू कैन जस्ट write down the chat box, or you can mute off yourself to is it clear or not? yes yes definitely somebody is asking दोनों करंट अलग है। yes, both current are different. this is the already I0 is already flowing. I0 is already flowing. okay, in additional मैंने क्या लिखा है? additional primary current. additional means पहले से कुछ ज्यादा एक करंट फ्लो कर गया और उस एडिशनल करंट को हमने क्या नाम दिया? I1 डैश। तो अब जो प्राइमरी में करंट फ्लो हो रहा है वो क्या फ्लो हो रहा है? एक तो नो लोड करंट का फ्लो हो रहा ही है, ठीक है, क्योंकि वो नो लोड करंट आपके जो फाई बनाने में मदद कर रहा है, ठीक है, और उस फाई को कम कौन कर रहा था? phi2। तो उस phi2 वो कम ना हो, वो फाई ये कम ना हो, उस phi2 को अपोज करने के लिए एक नया करंट, एडिशनल करंट उसने सोर्स से ड्रॉ किया जिसका नाम क्या है? I1 डैश। प्राइमरी करंट I1 डैश। Now this what is the role of this additional current? This additional current is used for restoring the original value of the flux in the core of the transformer so that V1 is equal to E1. इस additional current का काम क्या है कि वो जो flux phi है जिसको reduce कर दिया था phi2 ने, phi minus phi2 बना दिया था, उसको compensate करे और हमारा जो induced EMF है प्राइमरी में E1 वो maintain रहे, ठीक है। नाउ दिस प्राइमरी करंट इज इन ऑपोजिशन विद द सेकेंडरी करंट। ये चूंकि इसको फ्लक्स phi2 को अपोज करना है तो ये हमेशा किसके? phi2 को अपोज किया, देयरफॉर वी कैन इनडायरेक्टली वी कैन से दैट इट इज इन फेज अपोजिशन विद द सेकेंडरी करंट I2, क्योंकि वो वापस उतना एक फ्लक्स देगा, ठीक है, ऑपोजिट डायरेक्शन में जहां पर phi2 प्रोड्यूस हो रहा था। इसलिए दिस करंट इज आल्सो कॉल्ड प्राइमरी काउंटर बैलेंसिंग करंट। दिस I1 dash is also termed as an what? Primary counter balancing current. okay, अब क्या होगा? इसने ये कैसे रोल प्ले किया? let me explain this. The additional current I1 dash, okay, this also will produce its own MMF. ये अपना एक own MMF प्रोड्यूस करेगा। MMF क्या होता है? मैंने अभी डेफिनेशन बताई थी। इट इज मैथमेटिकली इट इज नथिंग बट प्रोडक्ट ऑफ नंबर ऑफ टर्न्स एंड द करंट। अब करंट कितना है? I1 डैश, और ये किसमें फ्लो हो रहा है? प्राइमरी वाइंडिंग में। किसमें हो रहा है? प्राइमरी वाइंडिंग के अपने कितने टर्न्स है? N1। therefore the MMF produced by this additional primary current which is called primary counterbalancing current will be N1 I1 dash। ये जो मैंने लिखा है, ठीक है, और ये अपना एक फ्लक्स सेटअप करेगा। MMF प्रोड्यूस हुआ, MMF प्रोड्यूस से क्या होगा? फ्लक्स। MMF एनालॉगस है हमारे EMF के, फ्लक्स है एनालॉगस है हमारे करंट के। जैसे हम EMF लगाते हैं, सर्किट क्लोज होता है तो क्या होता है? करंट फ्लो होता है। उसी प्रकार जब हम एमएमएफ लगाते हैं, मैग्नेटोमोटिव फोर्स, विच इज नथिंग बट प्रोडक्ट ऑफ N1 इंटू करंट N1 I1 डैश इन दिस केस, so it will produce a flux phi1 डैश, एक फ्लक्स प्रोड्यूस हुआ phi1 डैश, ठीक है। और ये phi1 डैश किधर फ्लो होगा? It will flow in same direction as that of the phi, but opposite to the phi2. ध्यान रखना, ये जो phi1 डैश है ये किधर फ्लो होगा? इन द सेम डायरेक्शन ऑफ द मेन फ्लक्स phi, बट ऑपोजिट टू द phi2। जैसे मान लो phi का डायरेक्शन ये है, तो phi1 का डायरेक्शन, phi1 डैश का भी डायरेक्शन इधर होगा, मगर phi2 का डायरेक्शन इधर होगा, ठीक है। और ये दोनों आपस में बैलेंस करेंगे ताकि हमारा मेन फ्लक्स कितना रह जाए? phi, और हमारा इंड्यूस ईएमएफ E1 रह जाए। सो द मेन पर्पस ऑफ phi1 डैश इज टू कैंसल द phi2। व्हाट इज phi2? phi2 की वैल्यू कितनी थी? phi2 किधर फ्लो हो रहा था? किसके कारण हो रहा था? सेकेंडरी करंट के कारण। और सेकेंडरी करंट किसमें फ्लो हो रहा था? सेकेंडरी वाइंडिंग में। तो phi2 क्या हो गया? N2I2। phi2 का जो एमएमएफ है उसकी वैल्यू कितनी होगी? N2I2। इज इट क्लियर? नाउ these two both are balancing each other. Why they are balancing each other? In order to maintain our main original flux phi. Therefore I can write down that N1I1 dash, that is the primary counterbalancing current MMF and the secondary MMF, both should be equal in order that your flux phi should be maintained. Or in other words, I can also write down I1 dash. When I will rearrange this equation, what I will find? I1 dash is nothing but N2 over N1 into I2, and N2 over I2 is nothing but KI2. It is clear or not? Okay, so this relation you have to remember it, that I1 dash is nothing but N2 over N1 into I2. Okay, or you can because this is a constant, the N2 over N1 turn ratio is a constant for any transformer, therefore we can also represent by KI2. But remember this, I1 dash, that is primary counterbalancing current, is equal to N2 over N1 into I2. तो magnitude कितना हुआ इसका? magnitude N2 over N1 into I2. You can find out the primary counterbalancing current. Have you got this point? आपको यहाँ तक समझ में आ गया है? तो tell me. If not, then I can again explain this. No doubt. I think so. There is only one student who is active, that is Sanjay Adhikari. Remaining all students are just for the formality purpose. They are, now I am getting, after giving this statement, now I am getting some answer. Okay. Until unless you are not active, because I have already cleared my BTech, everything is my clear. Just for your purpose, I am explaining this. And if you are not able to understand, then my all this thing is in vain. Okay. So, okay. Some response I have got, that now for conclusion you have got that whenever a secondary is loaded, जब भी हम secondary को load करेंगे तो primary में दो current flow होंगे. You just concentrate once again this, when I will load the secondary, I2 current will no doubt will flow through the secondary current, but the primary will consist of two components. One is the no load current, okay, उसके अपने पर्पस है, उसमें एक को उसको मैग्नेटिक फ्लक्स भी बनाना है और उसको एक कोर लॉस भी देना. इसके अलावा सेकेंडरी में चूंकि करंट फ्लो हुआ तो एक ऑपोजिट में एमएमएफ प्रोड्यूस हुआ, तो उसमें एक करंट I1 डैश, जिसको कहते हैं प्राइमरी काउंटर बैलेंसिंग करंट, वो भी प्रोड्यूस हुआ. तो मैं आगे से ये कहूंगा कि जो प्राइमरी करंट है, इट इज द which type of sum? The phasor sum of two type of current. The phasor sum of two type. देखिए मैंने ये बार लगा रखा है. अब आप देखिए, now the primary current I1, सेकेंडरी को मैंने कैसे रिप्रेजेंट किया? I2 के साथ. सेकेंडरी करंट वाज I2 and primary current is now, this is primary current. Primary current. And this is your, this I2 is secondary current. So the primary current is nothing but phasor sum of no load current. Okay, this is no load current, and also and I1 dash, that is what is the primary counterbalancing current, and I1 dash is also equal to, magnitude wise it is also equal to N2 by N1 into I2, N2 by N1 into I2. If you understood this thing, I think so there will be no problem in drawing the phasor sum. Rather than the vector, I have used the word vector. It is not vector, it is phasor. Okay, so do correct it. It is not vector, it is the phasor sum of the two current, that is no load current and the primary current, which is making this the total primary current I1. I think so it is clear. This is a very important equation, minded students. This is a very important equation. Whenever a practical transformer is in loaded condition, it will have two components. The primary current has two components, that is I0 and I1 dash. Okay. This I1 dash is the primary counterbalancing current. This I1 dash is the counterbalancing current. Okay, and I0 is the no load current. So when a practical transformer is under loaded condition, it has two currents which are added phasorly, not scalar sum is not there. Okay, algebraic sum is not there. They are being added phasorly to form the total current, primary current. So the primary current is consist of two currents. Is it clear? Counterbalancing current is I1 dash. Counterbalancing current is I1 dash. Adhikari, it is clear. Okay, fine. So now I have shown you. Oh, sorry. What? So I am just sharing. There was some problem was there. I'm sorry for that. Okay. So now I am placing before you the phasor diagram of a transformer when it is inductively loaded. Inductive loaded. Now here when I say inductive loaded, it means there is a resistance and inductance, both are there. Okay. So first of all, let me clear your first of all concept that when I say inductive loaded, what does this mean? That what is the voltage and current relationship? Phasorly, how you will conclude that what is the phase relationship between voltage and current? Anybody from your side? Okay, if this is my voltage, if I take this voltage as a reference, okay, now it is an inductive load, means you can assume it to be an RL load, not pure inductive, it is RL load. Okay, so where will be the current direction? If this V is my 0 degree, where will be the current direction? Tell me fast.
Vertically downward.
Not vertically downward, inclined downward.
From niche side.
Like this.
Incline.
Incline.
Yes,
Is
sir.
it clear? It may be some angle theta, okay, that will lie between 0 to 90 degree. Not 0, not 90 degree, but it will be some 30 degree, 40 degree, 45, 65, 75, 85, 87, like this. Is it clear? So this should be very clear. Now I will explain the phasor diagram. Okay. Now this is the phasor diagram in front of you. Everybody can see it. So you can see that I have taken phi as a reference. Okay, reference, my 0 degree line is this much. So this is reference, phi is reference. So what happens? Due to this flux phi, what will happen? Now, what will happen? This flux phi will produce an EMF, an induced EMF. Now this induced EMF opposes the cause, therefore it is shown in the downward direction, E1 and E2. This is shown in the opposite, they will oppose the cause, they will lag behind the flux, okay, because of the minus direction is equal to, because induced EMF is what? Minus dn phi by dt. Okay, this minus sign will put them in the downward direction. So flux phi is 0 degree. So E1 and E2 are being produced. Clear? Induced EMF is produced. Okay. Now what happens? A no load current will produce. A no load current is produced. Also, let this value is I naught. Okay, this value is I naught as shown in the figure. This is I naught is there. Okay. Now these two are clear. I naught is there. The flux phi is the reference. Induced EMF E1 and E2, they are in phase opposition to the flux. Therefore, they have been shown vertically downward, E1 and E2 at an angle of 90 degree. Now, let the terminal voltage V2 is lagging by an angle of, say, some of anybody, because these if you look toward the diagram, okay, then these two are not in phase with E2 and V2 are not in phase. They will have some lagging. So let this be V2. Now I have already told you that it is an inductively load. So the current will lag. Let the power factor be phi 2. Okay. So current will lag. So I have shown it here, current I2, secondary current I2. Okay. Now if I want to complete the voltage diagram on the secondary side to this V2, to this E2, sorry, what happens? This E2 is there is a something is direction is wrong is there. Now what happens on the secondary side? Let this is a primary, this is my secondary. So here E2 is being produced. Okay. Now the practical secondary transformer will have a resistance as well as an inductance. That because of that only it is lagging. Okay. If there is no resistance, no reactance, okay, then it would have not lagged. It will be in phase with the V2, but it is lagging because of the presence of this R2 and X2. So what will happen? That there will be drop across I2, this, and there will be drop across the reactance X2. Okay, and this will counterbalance. This will be equal to your E2. So to this terminal voltage V2, we have added a drop of I2 R2. Now this I2 R2, what will be the direction? What will be the direction of I2 R2? It will be in parallel with the current I2. So you can say this is the current direction. So this is your direction of the I2 R2. Okay. Now to this I2 R2, I have to add a drop due to the reactance X2. What will be the drop? I2 X2, and it will be at an angle of 90 degree with respect to I2 R2. So this angle is 90 degree and it will get added. So E1 E2 is balancing V2. So I can write down mathematically E2 phasor is nothing but equal to your terminal voltage V2 phasor plus I2 phasor R2 plus J I2 phasor X2. So this is a very important equation we have got. Okay, you have to understand that how my secondary is working. So first of all, I have drawn a reference phi. Due to this reference, an induced EMF which is at an angle of 90 degrees is being produced, E1 and E2, both in the primary and the secondary winding. And as soon as I connected a load being, I have assumed it to be a resistive inductive load, therefore a terminal voltage V2 is produced, okay, and the current I2 is being produced. This current is lagging by an angle of phi 2. Now this voltage drop V2, this terminal voltage V2, to that I have added the drop across the resistance of the transformer on the secondary side, and also added at an angle of 90 degrees the drop across the reactance of the transformer I2X2, and this is thus balancing the E2 voltage across the secondary winding. And this is the mathematical equation that E2 phasor is nothing but V2 phasor plus I2 phasor R2 plus J I2X2. So this is how I think so the secondary phasor diagram is clear. Now what happens on the primary side? A no load current is there, I naught. Now this even now to draw the phasor diagram on the primary side, what happens that there is a voltage is there which is maintaining even, and that is what voltage V1 dash, that is what V1 dash, that is what called V1 dash, which will try to maintain the even. So and it will be in opposition to the even, therefore I have drawn on this side upward. So we have a no load current, we have also an प्राइमरी काउंटर बैलेंसिंग करंट विच इज इन अपोजिशन टू I2. तो देखिए I2 इधर है, तो इसके जस्ट अपोजिट में हमने एक हमने I1 डैश बना दिया, ठीक है, ये जस्ट अपोजिशन में इसके ये इस प्रकार की लाइन है स्ट्रेट, ये अगर इस डायरेक्शन में I2 तो I1 डैश इसके अपोजिट में, ये ध्यान रखना, ठीक है। और ये दोनों I0 और I1 डैश ये दोनों मिलकर क्या बना रहे हैं हमारे I1 फेजरली, जो मैंने फेजर डायग्राम लिखा था, फेजर इक्वेशन लिखी थी, वो I0 और I1 डैश दोनों का रिजल्टेंट, टू साइड्स का बीच का जो होता है वो क्या होता है, रिजल्टेंट होता है, तो I1 डैश। नाउ I1 dash is being produced. Now I will draw the voltage. V1 dash is the nothing but equal to E1. But on that side, I have write down on the primary side. Therefore, I have write down this. Now this is in this I will add the drop across the primary resistance. That is I1 R1. Now this I1 R1 will be in phase with this total current I1. This is the direction. So it is parallel with this. Now to this at an angle of 90 degree, I will add to the angle of 90 degree. I will add I1 X1. So V1 dash plus I1 R1 plus I1 X1, and this will form complete my applied voltage V1. So this is the phasor diagram of an actual transformer or practical transformer or an non-ideal transformer when it is inductively loaded. Inductively loaded here means both resistance and inductive loads are there in series with each other. I think so the phasor diagram is clear. If not, you can interrupt me so that I can give you more detail about this. Yeah, somebody asks me I2 lead E2. In fact, V2 lags behind the E2. V2 lags behind E2. That you have to keep in the mind. V2 lags behind E2 because V2 is the terminal voltage which we have obtained when we have connected an inductive load. When we have connected an inductive load. So therefore definitely V2 will lag behind the E2 and I2 lags behind V2. तो देखो लैग का इधर चलता है, ठीक है, V2 इसे लैग कर रहा है तो हमारा ये लैग कर रहा है, इधर चला गया। अब I2 V2 से भी लैग कर रहा है तो ये इधर आ गया। You got my point? No, I2 is not leading. I2 is not leading E2. You are when I am going toward this side. Okay, if I am going toward this side, then it will be leading. I am going toward this side. You see, I am going toward this side. Okay, so here whenever I am going, if I talk in reference to this, then V2 is lagging behind E2 and I2 is lagging behind V2. Therefore, I can say I2 is also lagging behind the E2. You got my point, Adhikari? If you haven't understand, you can mute off and can sir please explain this point I haven't. So V2 is lagging behind E2, I2 is lagging behind V2. Okay, this is the phasor diagram. Okay, it is clear. Now this E2 is balanced by three drops. One is the terminal voltage across load, another drop across the secondary resistance R2, and another the drop across the reactive impedance, reactance of the secondary windings. Okay, so I have added them phasorly because this I2 R2 will be in phase with this I2 current. Therefore, in parallel with I have drawn it to at an angle of 90 degree. I have added I2 JX2 because it is J I2 X2. So J means rotating a phasor by angle of 90 degrees. So this is at an angle of 90 degree I2 X2, and these all three voltages are balancing my E2 voltage as per Kirchhoff voltage law E2. Okay, so this is complete phasor diagram on the secondary side. Now come to the primary side. Primary is drawing a current I0. Okay, and also and I1 dash, that is primary counterbalance, which is just opposite to the I2. Okay, and these two are phasally adding, forming an I1. Okay, now this I1 is causing, now this V1 dash is nothing but the corresponding voltage to the E1. So I have, because I have to show on that upward side, therefore I have shown in on this side, therefore it is V1 dash. Okay, V1 dash to this added I1 R1 in parallel with I1. ये देखिए ये I1 है, तो इसके पैरेलल में मैंने I1 R1 ड्रॉप ऐड कर दिया. अब I1 R1 में मैं J I1 X1 ड्रॉ करूंगा, ठीक है, यहाँ पे 90 डिग्री पे, तो ये ऐड किया, और ये पूरा ड्रॉप V1 डैश विच इज नथिंग बट इक्वल टू माइनस E1 प्लस I1 R1 plus J I1 X1 is equal to V1. So V1 is nothing but V1 dash plus phasor लिया plus I1 phasor R1 plus J I1 X1. Okay, and V1 dash is also equal to minus E1. Clear? Is it clear or not? Somebody has asked some question. Yes, the main flux, yes, very clear. This primary counterbalancing current is that in order to maintain the main flux constant, उसको phi रखना है. उसमें जैसे phi2 ऐड होता है वो डिक्रीज हो गया, तो प्राइमरी करंट ने कहा चलो मैं तुम्हारे लिए युद्ध लड़ता हूं और ये phi2 को कैंसिल करता हूं, तो नतीजा हमारा मेन फ्लक्स phi कांस्टेंट रहा. इज इट क्लियर? मेन है कि phi को कांस्टेंट रखना है. तो आज मैं आपको ये इंडक्टिव लोड के लिए मैंने बताया, कल मैं आपको कैपेसिटिव और रेजिस्टिव लोड का भी मैं फेजर डायग्राम बताऊंगा. प्योर रेजिस्टिव लोड हुआ तो क्या होगा, आप भी आज घर पे प्रैक्टिस करना, ठीक है. और एक कैपेसिटिव लोड हुआ तो कैपेसिटिव लोड में क्या होगा, करंट विल लीड. नाउ करंट विल लीड तो करंट इधर आ जाएगा, और रेजिस्टिव लोड में क्या होगा, प्योर रेजिस्टिव लोड में ये करंट इसके साथ जुड़ जाएगा. और अगर प्योर इंडक्टिव लोड होता तो क्या होता, ये पूरा 90 डिग्री होता. ये I2 है ना, यहां से इससे एक 90 डिग्री एंगल बनाता. इज इट क्लियर? तो अकॉर्डिंगली यू कैन ड्रॉ द फेजर डायग्राम. कोई डाउट? यस, मेन फ्लक्स को कांस्टेंट रखना है. कोई डाउट हो बोलो.
नो सर.
नो, सभी के लिए नो है, या किसी के कोई डाउट हो तो बोलो, बिकॉज ये वेरी इंपॉर्टेंट है. अगर ये मिस कर गए आप, देन यू विल नॉट एबल टू अंडरस्टैंड द होल मशीन. ओके, because this is a very important question from your examination point of view. Draw the phasor diagram of an loaded transformer when it is inductively loaded, when it is resistively loaded, when it is capacitively loaded. Okay, so this is a very important question from your examination point of view. That is why I am focusing it on. So I think so there is no question is there. Okay, so the strength is very poor. Okay, so be punctual, else we may have to take action against you because of your absence in the class. Okay, I have got only 40 students, so at least it should be approximately 70 students. Okay, so no doubt that I am ending this session. Thank you very much for joining with me.